Hello, welcome back. In this segment, I will briefly explain the core idea of sieve of Eratosthenes. It's a beautiful algorithm for prime number generation. It's an ancient algorithm. In this segment, I will just show you the Python implementation of this algorithm and explain the fundamental concepts behind this particular algorithm. Okay, suppose you are given a number n, say n is 5, and you would like to know all the primes below, including 5. Basically, the output should be 2, 3, 5. Let's run it through a demo first, and then I will talk about the core of the algorithm. You get 2, 3, 5 as the list of primes below or equal to 5. Okay, let's do the same for 11. So you get 2, 3, 5, 7, 11. And you get the idea, hopefully, that sieve of Eratosthenes is a very quick algorithm for small list of numbers. Let's say I want to generate all primes below 1000, including 1000. So very quickly you get the list of primes. Okay, so what is the core idea of this algorithm? The core idea is as follows. So what you have is basically, you can imagine like this. You have a bunch of numbers, say 1, 2, 3, 4, and so on, right? All the way until n. N could be any number, n could be 100, okay? Let's make it concrete. Let's say n is 20. So we have all these numbers. The first step of the algorithm is to take 2 as a prime, because we know 2 is a prime, and look at all the multiples of 2 and cancel out all the multiples of 2 from this list. Okay, so cancel out means any multiple of 2 cannot be a prime, of course, because prime means it should not be a multiple of any other number other than 1. So it means in the first phase, it will cancel out the numbers 4, 6, 8, 10, 12, 14, 16, 18, and 20 are out. They cannot be prime numbers. So what you're left with is basically all the odd numbers. Okay, so the next step is select the next prime number that's not canceled out yet. So 3 is not canceled out in the previous phase. So we'll take 3 to be the new prime number and cancel out all the multiples of 3, 18. You probably notice some of the numbers are canceled out multiple times. That's one of the weaknesses. Okay, but you get the idea that multiples of 3 are all canceled out. 4 is already canceled out by 2, so we will not pick 5 is the next new prime number because it's not canceled out yet. So it will cancel out 10, 15, 20, okay, which is already canceled out by previous numbers, but that's perfectly fine. And now 6 is already canceled out. So far in our prime list, we have 2, 3, 5, okay. This is the final list of output we will send out. I will add it here. 6 is already canceled out. 7 is not canceled out. So we will have 7. What are the multiples of 7? Only 14 will be canceled out. So we'll add 7 here. 8 is already canceled out. 9, 10, 11 is not canceled out. So 11 will be there. And we will cancel out 13. Well, 13 is not composite, so we'll have 13. 12 is cancelled out, I meant to say. 13 is there. 14 is cancelled out. 15 cancelled out. 17 and 19. These are the list of primes we will get if you run the sieve of Eratosthenes algorithm. That's the general idea. Okay, so now let me show you the algorithm itself in a more formal way. Okay, so the algorithm leverages a couple of theorems that we discussed in the previous segments. So here is the fundamental point that I would like to highlight is that what is the meaning of I times I less than or equal to n? Okay, that means I square is less than or equal to n, right? Which means I has to be less than or equal to root n. Why do we do that? Remember, if a number is a composite number, you will find its prime factors. One of the prime factors is less than or equal to the square root of the number. Okay, so if n is a composite number, let's assume n is a composite number for a moment, we will be able to detect it as composite by finding out a number I less than or equal to square root of n, because we proved in the previous segment that one of the factors must be less than or equal to square root of n. So we can leverage that. All right. So we assume I is a prime number when the loop starts, and then we mark all the multiples of I as composites. That makes sense. That's basically the definition of composites. Okay, so more formally, first we assume all the numbers are prime numbers. So this true means you can imagine all the numbers are marked as prime, and then we go and update the numbers that are composite by taking a prime number I and ruling out all the multiples of I as composite. That's what we are doing here in this for loop. Okay, and then once we are done with the for loop, we look at the binary array we have and figure out the first element which is marked as prime. And that means let's assume when our I is 2, the very first element of the next prime will be I equal to 3. So we will select the next prime, and we search for that. We found out that B of I is true, which is true for I being 3. We will break this inner while loop and continue to rule out all the multiples of 3. And then once you're done with this, the next I will be 4, but 4 is not a prime. So we will continue to make it to 5, and 5 is marked as prime. So we'll break the loop and then go here and multiply all the, rule out all the multiples of 5. Okay, that's basically the core of the algorithm. Okay, it sounds very simple, but it's very interesting from an analysis point of view. I will talk about the complexity later. As I said earlier, we will only run until I less than or equal to square root of n, right? And the question is, how many i's are there? How many i's we can easily predict, because we know the prime number theorem. If you are given a number n over log n numbers, right, to the base e are primes. So the fact that we are running for I less than or equal to square root of n tells us that we will be running this while loop square root of n log square root of n, right? And then we need to compute how many times we will mark b of j to be false. That's basically the further details that you will have to analyze, but you get an idea that it's kind of exponentially in the length of the number n. Okay, if n is say 2 power 1000 number, okay, then the algorithm will run, it's more than 2 power 500. Okay, I'm just making a very high level approximation very quickly, and it's not possible for us to store that many elements in a Boolean array like this. Okay, that will be impossible. No computer in the world can store that many elements in this Boolean array. That's one of the limitations of this sieve algorithm that I just talked about. Okay, there are many variants of the sieve algorithm if you look into the textbooks or internet. This is one of the basic ones that I thought to cover very briefly. Okay, so once we are done with this while loop, we can go ahead and final answer. So final answer is over here. So we go through the Boolean array and pick all the elements that are marked as true, starting from 2 onwards, because we know 2 is the first prime number. Recall that in Python, the for loop runs until n. If you put n plus 1, the program will run until n. That's the reason why we created an n plus 1 array here. Okay, because we start from array index to be 0. All right, to sum up, this is a very basic algorithm, very powerful algorithm. It's very useful for quickly generating a list of primes for small list. Okay, for example, 2 power 16, right? Very quickly we get all the primes below 2 power 16, as you can see, very quick. But it does become a problem as soon as you start increasing the number n value. Okay, that's all. Thank you very much for your attention.